All right, we can begin. Sorry about that. I had a problem setting up this workspace, but now we have the slides ready and we should be able to have a successful session going on. Okay, so this is going to be a lesson following up the introductory lesson that we had last week, or last week but one, when we introduced ROS and why we need it. This time round, we're going to go into the practical aspect, being able to work with packages and nodes, and more specifically, being able to work with the Robotics Dojo Docker image that we've been working on for the past 2 weeks, getting feedback from you as well. So I will move on to today's presentation. These are the topics that I aim to cover. I understand that time is not on our side, and part of that has been due to some unavoidable circumstances, but we'll make use of the remaining time and cover as much as we can. So we're going to look at Docker, we're going to look at nodes, more or less review what we did last week, and then get down to building our own packages. And finally, we'll talk a bit about launch files, which are going to be necessary down the line. Starting with, I'll talk a bit about my ROS experience. I have been the go-to ROS person for this period that I've been working with the Robotics Dojo participants. And even with that, I am not a ROS expert per se. I started working with ROS when I did my final year project on the KUKA robot arm. It's an industrial robot arm that was purchased by the school for research purposes. And for my final year project, I wanted to build a visual servoing application. So being able to control the robot arm using computer vision, that is a camera. And before I could get started, I did need a programmatic interface. And what I mean by that is that the robot arm is currently being controlled using a teach pendant, as you can see in the image. That is the robot arm's remote control. But for you to be able to automate that, you do need a way to get access to the robot joints programmatically. So write your own code to be able to move the joints and get the joint state. And for that, there is a tool provided by KUKA called I'm forgetting the name of the tool provided by KUKA. It's an IDE, basically like a Visual Studio that enables you to write a code in KUKA's proprietary KUKA language. So it's called a KRL or KUKA robot language, and it's used to control the robot, but it does not offer a very flexible interface for you to be able to write your own code. So the very first objective with this robot arm was to build a programmatic interface. So I did do a lot of work in establishing my own interface, and it's currently, you can be able to control this robot arm using ROS. At the time I used ROS1, there were not many ROS2 libraries for supporting this robot arm. And I ended up building some of my own libraries to work on ROS1 to be able to get that programmatic access and read its joint states as well as command it to move to different positions. Following on from that, I got to ROS2 because ROS1 is coming to its end of life and ROS2 is the future. So I started learning ROS2 and learning it in the objective of being able to also port the code that I wrote for ROS1 into ROS2. But that's still a work in progress. I'm still learning ROS2, and all of you in this year's competition, the Robotics Dojo 2024, are going to be required to use ROS2. So it is necessary for all of us to be familiar with ROS2. And even speaking to the topics that we're going to be discussing today, I am also looking at it coming from a ROS1 background. But as I've mentioned, I am still learning. I am in the same boat as you, maybe just a little bit ahead, given that I have read the documentation a couple more times than you have, but we are all in this journey together. Getting to the first part, this is Docker, and I needed to explain again why we are going to be using Docker and why Robotics Dojo decided to move forward with Docker as a base. as one of its software tools that we've incorporated this year. We did not use Docker last year, but given the lessons that we learned for the previous 2 years, we saw this would be a necessary tool in order to reach our broader vision. So I will go into the various reasons as to why we are using Docker again. And the first reason is portability. Generally, when working on robotics applications, or I should say intermediate to advanced robotics applications, you're going to be working with multiple systems. That is, you're going to be writing code on your laptop, maybe testing it on your laptop via simulation, and then deploying it on the Raspberry Pi or other single board computers like the Jetson Nano, for example. So given that you're going to have different architectures, you're going to be working with different systems, Docker provides a convenient way for you to be able to take your code and make it run anywhere, because from this terminology, there is something called a Docker container. So within that container, you have all the tools, all the dependencies, and all the requirements to make your code run as expected. So this makes Docker a very suitable tool. It's primarily used in software development. Those that have done software development and are in the software engineering field, you do know Docker is an indispensable tool, and for robotics, this is finding new ways of using this tool for our own benefit, and portability is one such benefit. The other one is isolation. This one might not make sense immediately, but I'll try to give an intuitive example. So usually when you're working on different projects, and I'll use, let's say, an Arduino project, for example, you will install a library. Let's say this is the library used to control the gyroscope. You'll install that library, you'll start working on it, and maybe that's one robot that you're building, get done with it, you start a new project building a different robot that requires the same library. But this time when you go to download the library, it has been updated because software keeps being updated, solving bugs, enhancing its performance. So you'll find that maybe in the Robot 1, you used the gyro library version 2.5, but with Robot 2, the gyro library is version 2.8. And due to the recent changes within that library, they are not backwards compatible. And what I mean by that is that 2.8 will not work for code written on 2.5 and vice versa. So being able to, and this when installed on a computer system might bring some clashing within the software ecosystem. So this is where you usually find that you are trying to run an application, but it is riddled with bugs. There are files that are missing, there are files that are required, and you do not know what is happening because it's not anything to do with your code, it's things to do with the dependencies. So being able to isolate these different requirements within a container gives you that benefit of doubt that this system is going to remain stable throughout its development phase and even after its deployment, given that new tools, new software won't affect what you already had within that container. So isolation is the next one. The third one is efficiency. Traditionally, when you are building such kind of application and you're looking for such kind of benefits as portability and isolation, you did use virtual machines, but virtual machines are resource intensive. And given that you've been doing some research in this particular area, you might have come across VMware or VirtualBox. Some of you might have used those tools to install maybe a different operating system within your laptop. And that is okay. People have been doing that for a while, but how virtual machines are architected makes them very heavy on your system. And in fact, if you try running a virtual machine in a laptop that does not have at least 4 GB of RAM, then you're going to be suffering quite a lot. 4 GB might not even be enough for your own laptop. So you can imagine trying to support an entire architecture on top of that. So Docker was built with this in mind. It was built to take over or to completely outdate the virtual machines, making them efficient, and you can actually run multiple containers at the same time without hurting your computer and without getting that lag. So quite efficient. Another reason to use Docker. The other one is consistency. This one is in line with the isolation. And for this, again, I'll go back to the Arduino libraries and the different software requirements. And the fact that you're going to be running these different Docker containers gives you that benefit of doubt again, that whatever software libraries you downloaded in one container will remain static and will not change over as you try to do different projects and as you try to experiment with different libraries. In fact, one thing you can do is in one Docker container, let's say you are in the navigation team, given that this year's challenge will require Slam and navigation. Given that you're in a navigation team, you might want to try out different Slam algorithms. So on one Docker container, you install a Slam toolbox, and that is what you use to do your Slam map generation and navigation. And the another one, you try out a different, and in a different container, you try out a different Slam algorithm. So this enables that quick and rapid experimentation, because afterwards you can just delete the container and get done with after getting your results. Finally, this is knowledge transfer. And this is specifically to Robotics Dojo. We've been noticing we are solving the same challenges every year. So if we solved line following in 2025, in 2022, coming on to 2023, we have a challenge that is more complicated, but with lines. Again, we start trying to solve line following before going to the challenge. So having this Docker repository where we're going to be building on top of what we learn, where we're going to be releasing packages as we learn new things, as we implement new features. This is going to save you time in terms of not repeating yourself. You're not going to be solving again line following while it was already solved. So you're going to start with packages that have already done that for you. And that is also one of the things that we've tried to do with this particular Docker image for Robotics Dojo 2024. We've installed multiple packages that you're going to be needing in building a robot. So you're not going to start completely from scratch. And that is in line with our goal to keep this knowledge transfer consistent and progressive across the years to come. We're going to go into the demo. So this is demonstrating how to download the Docker image and run it. Given that I was facing some issues just a few moments ago, I might not be able to showcase this completely. And part of that reason is that we have still not completed testing this image. It is still quite unstable. So I'm going to just walk through what will be expected of you once we have finalized our testing and have deployed it. At the moment, we do have the image that is built for two different architectures. We do expect that you're going to deploy your robot on a Raspberry Pi. So we do have a Raspberry Pi or a Raspberry Pi specific image, because the Raspberry Pi uses a CPU architecture that is different from your computers. So we do have one specific to the Raspberry Pi, and we have another image specific to the computers. But to make your work easier, you're not going to be able, you do not need to memorize which image is for what architecture. We have made it easier for you to be able to run this image and to download it. And all you have to do is Docker pull code with Lenny RDJ 2024. All you need to put is latest. And this will go ahead to the Docker repository. It will detect your current system architecture and it will pull the required image. So I have pressed enter to run this command, and you're going to see it starting to process. I am going to get rid of this, and I'm going to show you something that we've done and I'm very happy and proud of. So instead of going through that manual process of Docker pull, we've actually created a script for you that does this automatically for you. And this script, I'm just going to show you some of its content. It is complicated given that we are trying to make it work for all systems, but you do not need to read it. All you need to do is simply do run it start rdj2024.shell. And this is for people that are using Linux systems. For Windows, is going to be a bit different, and that will be demonstrated through the next resources that we're going to be sharing. So for people running the this on their Linux machines, you're going to be able to start this script. And it's going to automatically go ahead and download it for you. So as you can see, it was unable to find it locally because I've not downloaded it. And then it's going to go and pull from the actual Docker Hub repository where we have saved it. And this process is going to take some time. The image is quite big. It's about 5 gigabits. So we are going to have to wait quite a moment for this to run. But the benefit of using this script that we've created is that you're not going to, after pulling the image again, try to running the image so that you can have a working container. The script is going to do this for you. So once you type that start RDJ 2024, it's going to automatically pull the image, and then run the container. And within this image, we have added all those tools that you requested from our previous interactions. So we do have visualization tools like RVs, we do have simulation tools like Gazebo, we do have text editing tools like Nano and gedit. We do have all the build tools that are required for ROS. We've also installed Turtlebot that you can use to do the demo for navigation, as well as the entire navigation stack. So this image comes very ready with most of the features that you've requested for, still unstable as I've mentioned. So we're going to release it within the course of the week, but I cannot give you a precise timeline given that we still are discovering a lot of issues. There are a lot of unknowns, as others will put it. That concludes the demo on the Docker image, and we're going to be interacting more and sharing more resources in terms of how to work inside the container. But what we've done by introducing this script is more or less take that overhead of Docker away from you. So you're not going to need to master all these different Docker commands. All you need to do is just run that RDJ script, and it's going to automatically start the container for you, pull the image if it's not available in your computer. And this works the same way whenever you run it on the Raspberry Pi. So you're not going to need to think about Docker too much. We've found a way of making even the graphical applications work. Just running that script will do all the magic for you. So that's something that I'm very happy that we've been able to do with our team, the team SysG. Next, we're going to go into nodes and topics. We're going to briefly review what we did last week, and this is because this is what today's class is focused on. And nodes and topics are the main communication method in ROS. And here are a few definitions for you, where a node is simply an executable that performs computation. And what you can actually do is you can have a node that controls the robot motors. You can have another node that gets sensor data. You can have another node that performs the navigation. So think about nodes as different pieces of your robot or different functionalities of your robot. And how these nodes communicate and exchange information is through topics. So a topic is simply a communication channel used by nodes to exchange information. When you get into nodes and topics, you're going to come across this other terminology of a publisher and a subscriber. A publisher is simply a node that sends out messages, and then a subscriber is a node that listens for messages on a topic. And I have provided, and this is from last week's example, a visualization of how nodes interact with topics. So node 1 and node 2 are communicating through a topic, and this I have a publisher node that is a temperature sensor publishing on that topic called temp, and then the electric fan, which is basically a motor, is another node that is subscribed to the temperature topic. So again, that terminology of getting used to a publisher and a subscriber, that's just something that we refer to when talking about the different types of nodes or the different types of communication methods that these nodes are utilizing. The other example that we're also going to be reviewing in this particular demo will be the talker and listener example. This comes whenever you install ROS fully, and you're going to have access to it even in the RDJ Docker image. And I'll go to that for a minute. So on my system, I already do have Docker installed, ROS installed. Primarily, I do use Ubuntu 22.04. And so that means even without Docker, I can natively run ROS2. And I'm going to, first of all, you do need to source ROS2. But again, this is already taken care of in that image. You do not need to run some of these tedious commands. You've already solved that issue for you. And I'm going to start some extra terminal sessions here so that I do not have to keep moving between them. I'll have them already pre-sourced. Again, this is not something that you're going to be doing in the Docker image that is already handled. We're just going to go directly to running ROS2 commands. So the first thing I'm going to run is the demo Docker. So the structure of the command is that you first need to call ROS2 and then run to be able to run a particular node. And before you run a node, you have to tell ROS which package you're talking about. So you're going to see this in the next slide of this package structure. So I'm currently running the Docker node and in a different one. So this is a publisher. This Docker is publishing to a particular topic.
Hello.
And we are going to see.
Yes.
Yes.
I called you some.
Sorry, go ahead. I cannot hear you. I think maybe there's a problem on his end. Could the rest of the members confirm that we are good? Just react or text something. I'll be able to see it. Okay, it seems like the issue was on his end. I hope he'll be able to fix that. But moving on with our presentation, I'm going to now run the subscriber. So I'm going to again type ROS2 run demo nodes py. And this time I'm going to run the listener. So now as you can see, this is listening on that particular topic that this first node is publishing to. And usually we like to visualize this using RQT graph. But even if you do not have access to RQT graph for whatever reason, or you do not want to keep running this graphical application, you can always run the actual ROS command that is used to display the currently running nodes and topics. So you have the talker node publishing on the chatter topic, and then the listener node is listening to this topic. Simple enough. I think I will not close these ones because we're going to be using them. I'll just stop my nodes, clear my terminal, then go on. So the next part is on package management, and I needed to introduce this part on packages before we go on more hands-on on the nodes, so that you can understand not only the structure of the ROS commands, but also how the file system within ROS works. So going on, this is an overview of the steps required whenever you are working with ROS and you want to build your own nodes. So technically you will build, you'll create first of all something called a ROS workspace. This is simply a folder where you're going to be putting all your ROS code, okay? And then once you're inside that ROS workspace, you're going to create a package, and this package is going to hold your nodes. So you can have multiple nodes in a package, you can have multiple packages in a workspace, and you're going to see sort of a visualization of this in the upcoming slides. So once you've created your package, you've created your nodes, all that is left is to build and run. when working on this and when using this workflow, you're generally going to see a lot of, it might seem like a lot of repetition, but it's necessary. And the good thing is that some of the things you'll be repeating are not going to be too complex or not going to be too tedious to get into your systems. And I'll go right on to creating a package. So I'm going to go back to my terminal. Again, I'll emphasize that this is going to be more hands-on, as this is what you're going to be doing also when working on your own robots. Yes, you're going to be working with packages that have been developed by others. For example, the navigation package. It's one such package. There's another package called Move It package. That is a package used in controlling of robot arms. And there are many other packages that have already been created by the open source community that you're just going to be downloading and running and using. But for your case, apart from just using some of these packages, you're also going to need to create your own in order to get your own robot to perform as required or as per the competition requires. So I'm going to create the ROS workspace that I've recently talked about. So in Linux, how we do this is using the mkdir command or make directory command, and I'm going to call this my ROS2 underscore workspace. So this is something common you'll see even when going through the documentation. You're going to see ROS workspaces having this underscore ws at the end to denote that it's a workspace. And this command is simply similar to actually going to your file system and creating a new folder. And to show you that that is what is happening, I'm going to go ahead and do that as well. So as you can see, I am currently in my ROS2 underscore ws folder that we just created. And within it, I can create a new folder called src or source, and this is where all your packages are going to go. So if I go back to my command line and type ls to list the files in there, I can see there's that ROS2 workspace that we previously created. I can go into it, ls again to see the new folder that I created graphically using that graphic window that I just showed. And I can go into this src, and inside that source folder, there is nothing, as I can also clearly visually showcase in this graphical window. So going back, that is what is going to be required whenever you're creating a ROS workspace. The first thing is that you're going to create that ROS workspace folder, and then you're going to create a source directory, src, abbreviated as that. And then I'm going to move a step back into that ROS workspace. So I'm inside the ROS workspace folder, and I have the src folder inside that. And the first thing that you're going to do, we've created the workspace, but we do need to build it. So we're going to do something called colcon build. Colcon is a build tool used, or the build system used by ROS2. If you look at some ROS1 documentation, you're going to see something called catkin. So you're going to see that, but that is for ROS1. Catkin is for ROS1. Whenever you come across it, run away. Just use it as a reference, but do not go ahead and use that tutorial line by line, as it is for ROS1, not ROS2. So colcon build, and colcon has finished building. That was quite fast. It does not take more than a second to actually run that command. And right now, when you do ls again to list the files in this ROS2 workspace, you'll see that colcon has added a few more directories. And I can also visually go ahead and confirm this. So if I go back to my ROS workspace, we only created src, but by running colcon build, we have created, colcon build has already created these 3 extra directories for us. And now what we need to do is source that directory. And I am using a different type of terminal. So you might find in your case, you're not going to write source install setup.z shell. This is what I've written, zsh. most probably you're going to be doing source install setup.bash. So just something to note in terms of the differences between even these terminal systems that we're going to be working with. But Ubuntu does come with bash, so primarily you're going to be doing source install setup.bash. So once you source that directory, you're good to go. You've created your own package. Sorry, you have not created a package, you've created your own ROS2 workspace. Now we can go ahead and create a package. So a package needs to live within a workspace, which is what we've just done. And technically you are required to create your packages within the source folder or within SRC. So inside SRC, I'm going to run a ROS2 command to create a package, and this is ROS2 package create. And we have the build type. And when you say build type, you are declaring what type of package this is going to be. So there are two main systems. That's going to be Python and C/C++, which is what other people might prefer to use. I'm going to create a Python package for now. So when you are saying build type, you're just telling it what type of package this is going to be, or what build system this package expects, be it Python or C++. You can go ahead and suggest the license that you're going to be using, but again, you're going to see this later on, that you do not need to specify this right now. All you need is to run ROS2 package create, then specify the build type, and finally the package name. So I'm going to call this, and I'm following the documentation actually on this, PyPubSub. So ROS2 has gone ahead and created my package. Again, did not take more than a second to run. I can go back to the root directory, and in this case, the root directory is the actual ROS2 workspace. But before I go there, I'd like to show you what it looks like. So when you run that ROS2 package create command, it went ahead and created a folder called PyPubSub, and it includes the necessary files required by ROS within a package. So I can go into PyPubSub, and if I list my files again, you're going to see that it has created some files here. We can go ahead and look at that graphically as well, just so that we are on the same page. So that's our PyPubSub, and there we go. We have some extra files that ROS has gone ahead and created. So a little bit about this before we go on. So this is how the package structure looks like inside the source directory. So remember, we are starting from the ROS2 workspace, and then we go into SRC or source, and then inside source is where we run the package create command, which created our package with the following structure. So we have the package name as the root folder name here, and it also creates another folder called the same name. So if it was PyPubSub, you see PyPubSub twice. And then there's a resource folder, a test folder, and 3 files. So whenever you get this structure, you're going to be writing your nodes inside this my package, the second directory that was named after your package name. If I go back to that, or let's start from a graphical approach so that it's easier to comprehend. When you're going to, I'll start from the ROS workspace again, go into SRC or source, go into PyPubSub, you will see that it has created another PyPubSub. So inside this PyPubSub is where you're going to be writing your ROS2 nodes. So up to that point, it can get a bit confusing to get used to this structure and this way of working, especially if you're coming right from Arduino. And with Arduino applications, things are usually very straightforward in terms of just creating an Arduino file and going ahead to write your code. But with ROS, there is a certain system that you have to follow. And we can quickly recap what we've just done. So we started by creating and building the directory or the ROS2 workspace. And once we did that, we had to create a package. After creating a package is when we create a node. And you'll get into this habit of within each of these steps, you need to again call build and then source that particular workspace. So let's go ahead and just do that. I'm going to go back to the main folder. So I am inside ROS2 workspace again. I need to run colcon build. And this time it will take some time. It will take like 3, 4, 5 seconds to get done because you actually have a package inside. The last time we ran colcon build, it only took a second because there was no package. So it was basically building an empty workspace. So that took just a second. But this time around, because we have actually created a package, colcon build goes ahead and investigates the package, looks for any requirements, gets them installed if there are any, and then um, ensures that this workspace is ready for use. And for you to be able to start using this package, again, you need to source the workspace. So once you've done that, you are good to go. You can go ahead to the next step, which is creating the node. And you will notice actually after building the package using colcon build, some new files have been added. So if I refresh this, maybe it's not working in this demo, but technically after building a package, there are some more directories that are added, but those are usually not relevant to you. They're just relevant to ROS in order to know how to work within that package. So all you need to worry yourself or concern yourselves with is this folder that I had shown you earlier. Let me go back to that slide. You need to worry more about this secondary directory that was created after running ROS2 package create and this setup file. So the rest of the files that are created by ROS, while it's good to know what they do, they are not necessarily required for you to be able to build and run your own nodes. So next, we're going to go into how nodes are created. So I'm going to go, where am I? I'm just going to type ls to look at where I am. And if you're using Windows, in the Windows command line, I guess the command that is similar to ls is dir. I think that is what shows you like the contents of the current directory. In Linux, it's ls, and I believe in other systems you're going to find different commands. So they get used, you get used to them after a while. So not ponder too much about that. Pub/sub. So I am inside that secondary folder. So remember when you created the package, it was given the package name was the first folder, and then it created another package, another folder within using the same package name. And inside here, I'm going to actually download an example by ROS. I found this in the ROS documentation, and this is actually what we just ran, that talker and listener demo. So I'm going to paste the command that have been given by the documentation, and what you're going to find is that we've downloaded a new file. This is provided by ROS. Again, these resources will be provided, but all that is important for now is getting into this file and seeing what is actually happening. So whenever we run ROS2 run demo nodes, and then we either opened up the listener node or the talker node. So what does that code look like, and how can we go about writing our own? I'm going to go into the root folder so that I can open up my command, my code editor. I primarily use Visual Studio Code or VS Code. I'd recommend it because it has a lot of tools, especially when it comes to working with Docker. Let me just increase the font size so that you can be able to see this through video. I hope that is large enough. I'll close the welcome window, and it is still initializing, so it might take some time before this extensions that I have finished loading. So as you can see, for example, one of the extensions that I've added on my VS Code editor is the Docker extension, And this gives me a very simple way of running my own images and running the containers, starting them, stopping them, getting access to Docker Hub, for example. So I do highly recommend if you are going to be using VS Code, to install the Docker extension and another extension called the remote SSH. I'm going to share details on this, especially when you get to working on the Raspberry Pi. The VS Code makes it very, very easy to attach this editor onto Raspberry Pi and be able to work within that interface. So this is my ROS2 workspace. Inside source, there is the first pub sub and then the second pi pub sub. And within it, I can see my publisher file that I've just downloaded. Before we even get to the actual code, let us start with the package.xml, as this is much simpler to digest. So this is created by ROS. Whenever you created that package, you don't need to create this. You just need to come here and confirm that everything checks out. So for example, the name of the package, you can publish the package version. You can maybe say this is version 1.0.0. And then one thing that you have to do is to type in a package description. So in this case, I'm just going to say is a demo package and license. In this case, what we've been using so far is the MIT license. And what we mean by licenses, this refers to open source licenses. And we are going to share maybe a link where you can go read more about the different licenses. But by now, I think you might have come across different licenses such as MIT license, Apache license, Creative Commons license, and you might have even heard sometimes there is this royalty-free images, there is this music that you can use on YouTube videos versus music you can't because they are not licensed, they're not open source licenses. So this general discussion of this topic about licenses is something worth looking into, especially if you intend to do commercial projects. You might get into trouble if you're not using the right license type. But for now, MIT is a good one to go with. This means that what the MIT license entails is that this is a fully open source project. Anyone can use it. Anyone can make money off of it. I'm okay with that. And so they don't even need to say that they got it from me. So MIT license is very, very open. And then, the other thing is you need to write in your name and the email. So this ROS picked out from my system automatically, but you do need to come to this package.xml and ensure that you have set in the right descriptions for your package, especially when you share these packages and someone comes across an issue, they might want to reach out to you. So they reach out to you by going into this file and looking at who is the actual maintainer behind this package. The other thing that, especially for Python, because we remember when you created the package, we said that the build type is amend Python. So it does come with this setup.py, and again, same thing, edit out the version, ensure that the maintainer and maintainer email is the same as package.xml, and then do the package description as well. And then the license, I did specify MIT, and you are done. So this setup.py file is going to be important when you're building these nodes, and you're going to see an example of that. So let's now go back to the file that we just downloaded from the ROS examples. And you can see here's another different type of a different type of license. Here they're using an Apache 2.0 license. Again, something that you might want to go and find out more about before you use, let's say, this code to build something commercial. I hope this font is large enough to be visible via video, but here we are importing RCL-Pi. The one for CPP will be RCL-C or RCL-CPP, sorry. So because we're using Python, we're importing the RCL-Pi, which is the ROS2 sort of library that enables you to write Python code. And then here we are importing the string data type. If you have done some bit of programming, you do know that there are different data types. So there is an integer, there is a string, there is a floating point number. There are many, many types, and ROS does come with its own data types. For example, if I am sending an image from one node to the next, how is that image communicated? What data type do I use to represent images? What data type do I use to represent LiDAR data? Because LiDAR data is a very unique type of data. So ROS does come with their own data types that you'll come across in the documentation as you get building. And even some of the examples that you see from the navigation stack that will be presented by Kenny, the second class on the navigation stack will be presented by Kenny, and you'll be able to see some of these things more practically. So once we get down from there, some of these things within ROS are not hard because ROS itself is hard. They are hard because they combine a lot of concepts. And one such concept is, for example, the concept of classes. This is something called object-oriented programming, where you have a class, and the class is, most examples say a class is a blueprint, or it's like a plan. And then an object is the actual, I want to use object again. An object is the instantiation of a class. So some of these concepts are not difficult because they are unique to ROS. They are difficult because they require you to have some good background knowledge on the actual programming language that you're using. So for now, in order to understand, let's say, this piece of code, you do need to know that this is actually object-oriented programming, and there are concepts here that are specific to Python, for example, or to another different, if it was in C++, you would see a different representation of this. And it's not that this is not actually ROS code, this is Python code. The only pieces of ROS that you're going to be using, you're going to see them internally here. So the best way to learn about these things is simply take pieces of code like this. For example, go on to ChatGPT or Bing Copilot or some of these other large language models and ask it to explain line by line what this means. It will go a long way into enabling you to write your own publisher code, your own subscriber code, and your own package in general, because you'll find that these concepts are not hard because they are ROS specific, but they might look hard because they do combine a lot of concepts. And using something like a large language model like ChatGPT will enable you to decompose everything and look at every single aspect to understand how everything comes together. So in this example, we are initializing a publisher. Remember, we imported the node from RCLPy. This is provided to by ROS because we want to create a node, and we define the publisher. So within this particular parentheses, you're going to see the data type. In this case, it's a string. And then here's where you specify your topic. So previously, we were using that talker topic. This piece of code here creates a timer. So remember, when we ran that talker code, it was publishing a message every so seconds. I have to go back to that just so that we now have an example as we're looking at the code. So you can see this message is being iterated every, I think, half a second or so, and that is what this code is doing. So here we are specifying that it's going to be running 0.5 seconds. And then here's what's called a callback. So we've created a timer, and once this timer triggers, so after every 0.5 seconds, something must happen. After every 0.5 seconds, something must happen. And maybe let me put this 1 so that 0.5 is just too much to say, to speak out. So after every 1 second, something happens. And that something is what we call a callback. So as you can see, whenever we created the timer up here, we are specifying that after a particular period, we want it to call this timer callback. It's why it's called a callback, because you call it or you trigger it. So after every 1 second, call this function here or this callback. And all it's going to do is append a number after the message hello world and go ahead and publish it. So what we are seeing here is that we are publishing the message hello world with that number appended afterwards. Then we have the main function, and what this main function does is simply set whatever we've described up here. So we initialize RCL_pi, we start our publisher, and then we tell ROS to go ahead and run this forever. So spin will ensure that that node runs until we go ahead and manually terminate it. So in this case, by pressing Ctrl+C, I'm able to shut down this node, and that is because this RCL spin was running it continuously, and then whenever you do Ctrl+C, this is the code that is run, and it is able to shut it down. This is an explanation of what happens behind the scenes for that talker node. We can go again into the listener node, and code will remain similar. And I'm actually going to go ahead and do that so that we take a look at both sides, and then I think that will be enough for today. So src pipub_sub pipub_sub, and then I'm going to run the command provided by the examples. And if I go back, you're going to see that I now have a subscriber function here. So let's just go into the subscriber file. Again, we have that license description. We are importing the same things we were importing last time. So you're basically going to be copy pasting most of this code. And then here we're creating a subscription. So we are saying that we are subscribing to a topic. In this case, we can call this topic again. Sorry, the actual topic was charter. If we go back to our examples, let me see if I can find it. Yes, this is the diagram I'm referring to. So we have a talker node, we have a listener node, and then charter is the topic name. So you do need to ensure that that topic name is similar in both the publisher and the subscriber. So this is going to be charter as well. And we are also going to make things consistent. So this line defines the node. We are going to call this our talker. And you're going to come here to the subscriber and call this our listener. Again, just using guidance from this, the example that was run by ROS. So again, we define our callbacks, and this what this is doing, for example, is whenever it gets a message in this particular topic, this is the function that is run. So in this case, it just says I had, and then the actual message, which is what we saw in that example that we ran. So we have the talker publishing the message, and then we have a listener listening to the message that is being published on that particular topic. So this is what I'm referring to. I had, and then the message itself. The main function simply does the same thing. You initialize RCL_pi, you initialize the subscriber, and then you cause it to run forever until I press Ctrl+C, which is when I break it, and then this is a piece of code that is ran, and ROS shuts down that node. So I'm going to go back to the terminal. We have, oh, and before we even go back to the terminal, the other thing that you need to do once you've created your nodes is go back to the setup.py and then edit this part. So there's this thing called an entry point. And this entry points, basically after you've edited this entry points part of the setup.py file, this is what tells ROS what code to run whenever you run that example. So when we say ROS2 run demo nodes by listener, ROS is going to go into your setup.py file and look at what is listener, what does this person mean whenever I need to run listener, where is this listener located? So That is what ROS expects to find in this setup.py file. So I'm going to go back to my example. I'm just going to copy paste what's provided in the documentations, but I do not spend too much time. So whenever you run ROS2 run demo nodes by Docker, it knows that's supposed to go to this pipehub sub package, and it's going to go into this node called publisher member function. That is the actual name of this file, as you can see up here, publisher member function. And then it's going to run this main function, as you can see in this file description. So if I go back to my setup.py, it's referring to this. So whenever I run in the command line ROS2 run demo nodes Docker, ROS2 is going to come into this setup.py file, look at what Docker is. So it knows that it needs to go into your package, and within that package, it will find a particular Python file called publisher member function, and within that file, there is a main function that runs that node. So this is what ROS2 expects to find in this particular setup file. And then we are going to do the same for your listener. So we do have a talker node and a listener node. So I'm going to come here and publish my listener. And then after this, you're going to call conbuild again, and then run your node. That section took a little longer than I thought it would, but I hope things are a bit clearer. Again, we're creating and building the ROS2 workspace, create the package, create the nodes, build and run. And running is when we type that command ROS2 run and then whatever is required. Finally, as I mentioned, you can have multiple packages within a workspace, and you can have multiple nodes within a package. So this is a representation of that. So assume this is the top level folder is the ROS2 workspace, and then inside the source directory or SRC is where we created our first package. And the other thing to note from this example is that you can actually have different types of packages. So you can have one package in CPP, maybe because one member of your team is proficient in C++. So create a package using the CPP build tool and write whatever nodes you need to write using CPP. If you are a person proficient in Python, you can create another package within your workspace using the Python build tool as we've just done, and then write your nodes using Python. So ROS does allow you to have different languages or different build systems within the same workspace, making it very flexible for every member involved. This is the kind of flexibility that is not available when you're using Arduino and other microcontrollers, but it's something that's going to get used to when working on production level systems. The final bit that we were to go through is the launch file, but I'm going to skip this for next time. And the inherent benefit of launch files, this is something that you just need to know and you're going to understand right away, is that launch files provide a way of running multiple nodes. So in the terminal, I had to go and write ROS2 run talker, ROS2 run listener. You can imagine if my robot had 5 different packages, and within those 5 different packages, I have 20 different nodes for the different sensors and the different actuators. It's going to take quite the number of commands to run. I'm going to have to open 100 terminal sessions and run ROS2, ROS2, ROS2 in all those sessions. So what a launch file does is you're simply going to that launch file, and it's simply a Python file, just the same way that we did with the setup.py, similar to how we did here with the setup.py. Maybe I can just visualize this for you. Similar to how you wrote that definition in the setup.py, is the same thing you're going to do within a launch file. So go to your launch file and tell it, I need you to run the talker node, I need you to run the listener node, I need you to run the motor drive node, I need you to run the ultrasonic sensor node. So all these different types of nodes. And then all you need to do is simply launch that one file. You're simply going to type one command and it's going to go ahead and run all those different nodes. So this is going to become very important as you start building the robot, as your software stack becomes more complex, as you get more and more nodes. Launch files are a way to consolidate all that into one command and run your entire robot. So yeah, it's going to be important to know how to write this. Thank goodness we are much simpler than what you've actually done with creating nodes. And once you get into this flow of creating a package, creating a node, doing the necessary setup within those setup files, and running it, you are done. That is a majority of what ROS entails. The rest of the time, you're just going to be finding bugs and fixing them and ensuring your robot runs as expected. So that will be the end of today's session. It has taken an hour. I actually expected it to take 45 minutes, but um, from my interactions with some of you, this is a topic that did require some revisiting, did require a little more time to be able to understand, a little more examples, to be able to get into that ROS workflow. So I hope that this session, despite the challenges that we faced and that we keep on facing with the Robotics Dojo Docker image, that I hope this session has remained helpful and resourceful. It has been recorded, so it will be shared on the Robotics Dojo YouTube channel shortly. And I will also share these slides as well as some of those resources that I have talked about. We are still going to be available. Feel free to ask questions within the various media, whether it's via the YouTube channel or via Discord and the other communication channels that we've established. If you do have a question right now, please feel free to either type it in the chat box or unmute yourself and ask. So I'm going to stop speaking, maybe listen to you, listen to your feedback, listen to what you need to know, or maybe what's bothering you before we call it a session.
Okay, Mr. Lenny, I have just one request, not a question. I hope you can hear me, right?
Yes, I can. Go ahead, Mohammed.
Yeah, okay. I was requesting maybe this is a very nice resourceful information, and also I see there is a great work here. So will you be in a position to share with us via any way so that we can also try to maybe go through it again? Either the documents, of course the video recorded and everything, plus even
Yes, all will be
some of the
shared.
codes.
In fact, we're going to share even a lot more than what I've talked about. So even in the last slides that I shared, I did put a list of links that you could go ahead and go do more reading. But we are also going to be, and some of the team members have already started writing blogs for Robotics Dojo. We do have a Robotics Dojo blog board that you're going to be posting some of these things that we're talking about. And that is one of the other ways we're going to be sharing what we have. So you're going to have access to everything, including the code that we run. In fact, the Robotics Dojo Docker image is also going to have a demo workspace with a package inside that you can go ahead and look around and try running so that you can understand what is going on. So yeah, you're going to have all the resources that we can provide, and always feel free to find a way to not only ask around how to use these resources, but also maybe you have an idea about how we can improve them for people that might not maybe understand a particular concept, or there's a different way we can um, go about sharing of these resources. So yeah, please feel free to share ideas, feel free to share areas of improvement in as much as you're going to be learning from what we've done. We also do need feedback from you so that we can create a very efficient process within Robotics Dojo. So yeah, thank you for that, and we'll surely will share the resources that you mentioned.
All right, thank you so much.
All right, any other question? Okay, I'm going to assume the silence means that we are good. Feel free to reach out to me however you can, and I'm free to share with you and to help you even within your robotics, the different groups that you've formed for your robotics teams. I am happy to join your teams and be able to provide help wherever you come. Some errors or some bugs that do need a bad eye. So yeah, feel free to reach out is what I am getting at. Otherwise, thank you all for attending this very long session. I hope you've enjoyed, and yeah, I hope to see you in the next one. Goodbye, everyone.